For medications to work effectively, timing is everything. Take a drug too late and it might not work. Too early and it could be dangerous. Chemistry gives us the tools to understand how medications behave in the body, how they're absorbed, metabolized, and eliminated, helping us design safe and effective treatment plans. Let's explore how understanding reaction rates lets us get the timing just right. This is Real Chem. Chemists need to know the difference between differential rate laws and integrated rate laws. When we plot concentration versus time, reactions of different orders produce unique curves. Understanding these patterns and knowing how to analyze them is an essential skill. These rate laws help us determine how quickly reactions occur, predict outcomes, and guide real-world decisions like drug dosing schedules. Let's break this down and see how kinetics impacts medicine and beyond. Let's say my mother takes two medications, one every 12 hours and the other every 8 hours. The timing difference is simple. We need to keep the drug concentrations in her blood within a safe and effective range. After each dose, the concentration starts at the upper limit and gradually decreases as her body metabolizes the drug. For the first medication, this drop reaches the lower limit in about 12 hours, signaling it's time for another dose. The second medication metabolizes faster, requiring a dose every 8 hours. The key factor here is how the drug concentration decreases between doses. This decline happens because the body metabolizes the drug, a chemical process we can analyze using kinetics. Using kinetics, we observe a straight line relationship between the concentration and the time for the drug taken every 12 hours. This means the concentration decreases at a constant rate, a zero-order process. Since the decay is linear, we can determine the reaction rate by calculating the slope of this line using y equals mx plus b. It is a zero-order rate law which creates a straight line relationship between concentration and time, meaning the concentration decreases at a constant rate. This allows us to predict when the drug will reach the lower limit of the target range and when the next dose is needed. This consistent decline is a key characteristic of zero-order processes. Now that we've explored zero-order processes with the 12-hour medication, let's examine the drug taken every 8 hours. This drug follows a first-order process, meaning its metabolism doesn't occur at a constant rate. In first-order reactions, concentration decreases non-linearly over time. The curve starts steep and then it gradually flattens. However, we can simplify analysis by plotting the natural log of concentration instead of concentration itself. When we do this, the data forms a straight line, making it easier to determine when the drug reaches the lower limit of the target range and when the next dose is needed. This straight line relationship between natural log of concentration and time is a key characteristic of first-order processes. In second-order processes, the concentration versus time plot is also nonlinear. However, plotting the inverse of concentration against time creates a straight line. If my mother were prescribed a drug metabolized through a second-order process, we could use these inverse concentration plots to adjust her dosing. This straight line relationship between 1 over concentration and time is the defining feature of second-order processes. Thus far, we assumed that we know the reaction order. This told us what to plot versus time. Now, we'll reverse the process, using these plots to determine the reaction order. By analyzing concentration versus time data, we can test whether a reaction follows zero, first, or second-order kinetics. Let's apply this to a test trial of a new medication, XR42. The initial data suggests it could be either first or second order. To confirm, we graph both the natural log and the inverse of concentration versus time graphs. Since the natural log of concentration versus time plot is the most linear, we conclude that XR42 follows a first-order reaction. Understanding differentiated and integrated rate laws matters. It will help you get through this course, sure, but it also helps us manage disease, keep medication effective, and keep people healthy. Chemistry is amazing, so go out and explore it. Thanks for watching.